Okay, I think it is time to start. So, if you recall, yesterday I finished in somewhere like non-existence and non-uniqueness of solution. Okay, and of course, this is concerned with your first order quasi-linear PDEs, right? Okay, so if you recall, I was considering a PDE of this form, okay? And you know where PQ are their functions of x, y, z, of course C1, okay? And defined in some region omega tilde in R3, and then what happened? We prescribed some initial condition. We considered a curve. We considered a curve C, and which is parameterized by this equation, right? And then we considered another curve C tilde, which is parameterized by Z naught t, and Z naught t is such that it is something like what? Z naught t. Okay. What we did, we defined this Z naught t along this curve C, and then I think Z naught t, it was defined as some functions of something like this, okay? And then what we have to do, we have to seek a solution of this differential equation, right? Okay. So yesterday we did when you were given a condition that your P x naught y naught z naught dy naught dt and minus q x naught y naught z naught dx naught dt, and of course we were evaluating these derivatives at the point t equal to t naught, which I mean this point, which this point your x naught y naught z naught in R3 on C tilde corresponds to. Okay, you all know this. And yesterday we did it for when this was not equal to 0, right? We found that there is a unique integral surface for this equation under the given prescribed conditions if this not equal to 0 is satisfied. So today let us do it for when it is equal to 0, right? And as I have told you yesterday, that what happens if you want to like say suppose your J is a solution of this equation. So now if I want to find out, say, dz dt along the curve C. So then, as I have told you, this will be nothing but your dx naught dt plus this, right? At the point t equal to t naught, or at the point x naught y naught j naught. So then, what is going to happen under this condition? What is going to happen? Like, because if you look at this condition, then you can see that this is simply what? dt by p, sorry, dx naught dt by p. It is going to give you this, isn't it? Is it okay?
Yes, sir.
Okay, so if I assume that this is some non-zero scalar, say mu, so then what is going to happen? So this is going to give me, for this, it is going to be simply mu p, and for this, it is mu q. So this is simply going to give you, right? Okay, and if J has to be a solution of this, if J has to be a solution of this, then it must satisfy this equation. So that is why this is equal to mu r. Is it okay? Fine. So, and of course, I am evaluating everything at the point x naught, y naught, j naught, right? So that means in order for this equation, to have a solution, I must have, along with this condition, I must have the third condition, say dz dt, of course, I mean evaluated, and I can consider this as j naught itself, because eventually what we did, this j naught we have already defined along the curve C. So if this is equal to mu, then this equation possesses a solution. If not, it doesn't. Is it okay?
Yes, sir.
Right? So if this is not equal to mu, this equation doesn't have a solution. So it is a case of no solution. So in that case, what is going to happen? Say, as I have told you that I have already been given this condition. Okay. So that means if, like say, on the curve, say this is a C tilde, and suppose this is the point x naught, y naught, j. Say, suppose I have this tangent, which I define it as say r prime t. You know that its component is simply dx naught dt, dy naught dt, and dz naught dt. Right? Fine. So now the vector b, what it is? Vector b is given by your PQR, right? So now under this condition, what is going to happen? You can write, I mean what? P to be equal to 1 by mu d x naught dt, and q to be equal to 1 by mu dy naught dt, isn't it? Is it okay? Fine. So it is something like it is going to be something like this. So far so good. Is it okay with everybody?
Yes, sir.
Right? So now let us see, I mean, what happens in this 3D space. So my situation is something like this. Okay. So suppose this is my curve C on xy plane. This is my curve C on xy plane. Okay. And suppose this is the point x naught, y naught. So then what is going to happen? Suppose this is r prime t naught. This is r prime t naught. So obviously now here if I draw a tangent, okay, so the projection of this line, obviously it has to be a tangent here, right? It has to be a tangent here, and that I have denoted by say r t naught. Okay, small r t naught. Is it okay? Fine. So now, what is happening? What is happening if your dz not dt by r, this is not equal to mu. This is not equal to mu. Then see whether it is equal to mu, it is not equal to mu. You always know that. You always know that the first two components of V is always proportional to the first two components of R, isn't it? Right? Is it okay with everybody?
Yes, sir.
Yes, sir.
Yes, sir.
Right? So that means the projection of V on XY plane, it is always going to be a tangent to the curve C at the point x0, y0, isn't it? At the point x0, y0, right? Are you getting my point? Because of these conditions, irrespective of whatever happens here, right? Whatever happens here, what we are going to get? The projection of this vector V on xy plane, it is always going to be a tangent to the curve C at the point x0, y0. Fine? Okay? So now, what is going to happen if this is not equal to mu? If this is not equal to mu, so that means the direction of V and capital R prime T naught, it is different. You got my point? Isn't
Yes,
it? Right? So that means I am going to have something. Let me just draw it a bit. Yeah, so I'm going to have something like this. I'm going to have something like this for V. In the third component, it is going to be different. Is it okay? Fine. If not, if this is equal to, I mean, mu, so both of them are going to be in the same direction. Are you getting my point? Isn't it?
Yes, sir.
Yes, sir.
They are going to be in the same direction. They are going to be in the same direction. So in that case, what is going to happen? Because in that case, I am simply going to get this also as, I mean, dz not dt, right? Okay, so that means what is going to happen? This is simply going to be equal to mu, right? Isn't it?
Yes, sir.
Fine. So that means V is what? V is a tangent to the initial curve C tilde at the point x0, y0, z0. Right? Isn't it? Right? So that means C tilde will be an integral curve, at least in the neighborhood of the point x0, y0, z0. Are you getting my point now? For the vector field V. Yes?
Yes, sir.
So we already know that in that case, the given equation P zx plus Q zy equal to R, it possesses an infinite number of solutions. And we know how to find out the solutions. Is it okay with everybody now? Yes?
Yes, sir.
Sir, the last part, can you please repeat? If the dz not dt direction and r prime t is not same direction, after that?
Okay, okay. See, like say, I have already assumed that this is always true. Okay, so irrespective of the third component, irrespective of what I mean, this divided by R, whether it is mu or not, I know that the projection of the vector V on the xy plane, it is always going to be what? always going to be tangent to the curve C lying on xy plane at the point x0, y0. Is it okay?
Yes, sir.
Right? Because if you take the projection of that, its third component is simply 0, isn't it? Right? And I know that the first two components, I know the first two components are simply proportional to the components, first two components of the tangent vector, isn't it? Right? Obviously, you know that the projection of this tangent vector is always going to be a tangent to this, isn't it?
Yes, sir.
Right? So, irrespective of whether this condition is satisfied or not, I am always going to get this projection of V on xy plane as a tangent to the initial curve C lying on xy plane. But if this is not equal to mu, so that means V is not along the direction of this tangent. So that is where you are going to get this kind of situation. Okay, fine. In that case, we are not going to have any solution. No solution. That means it is a case of no solution. Okay. And then if this is equal to mu, as we have already seen, that your V is going to be tangent to the curve C tilde at the point x0, y0, z0. So that means C tilde, at least in the neighborhood of x0, y0, z0, it is going to be an integral curve. It is going to be an integral curve to the vector field V. And so, by a previous theorem, we are going to have infinite number of solutions. Is it okay?
Yes,
Is it okay now? Okay. But still, you are not sounding confident. That yes, sir was kind of hesitant. You please go through again. Anyway, you can watch my recording. Please go through it again. It is not very difficult to understand. Okay. So I am going to do a couple of exercises. Okay. So this consider this equation jx plus yz, this is equal to x. Okay, and the initial curve C, suppose it is given by say t, suppose t greater than 0, So what you have to do, you have to check the possibility. When case A, your z equal to 2t on C, B, z equal to t on C, and C, z equal to sine pi t by 2 on C. Okay? Fine? Yeah, can you tell me? Of course, like say here, p equal to j, q equal to y, and r equal to x, isn't it? Fine? So if I want to find out your p dy not dt minus q dx not dt on the curve C, so then what it is going to be? On the curve C, what? P equal to j equal to 2t, isn't it? Fine? And dy not dt, because this is x, this is y, x naught, this is y naught, right? So that is equal to 1, and q equal to what? Y. Y on C is t, right? So this is t, and what this is? Dx not dt. This is again t, right? Isn't it?
Yes, sir.
Yes, sir.
Right? So this is 1. So what we get? This is t, and we have already given t greater than 0. So that means this is not equal to 0. Right? This is not equal to 0, isn't it? So we are going to have a unique solution in that case. Okay, fine. And then in the second case, z equal to t. So in the second case, if z equal to t, so then instead of 2t, it is going to be t. So this is going to be 0. Right?
Yes,
Isn't
sir.
Yes.
Right? And in the third case, and of course, I think I missed a part of the question. Another part is that you are told to find it in the neighborhood of 1, 1. So in the second case, anyway, this is going to be 0, right? This is going to be 0. And in the third case, in the neighborhood of 1, 1, this is again going to be 0, isn't it? Because it is going to be sine pi by 2, right? When t equal to 1. Okay, so that is 1. So eventually, and again, this t, I mean, like, just a minute. This is also going to give me 0, isn't it? Are you getting my point?
Yes, sir.
Right? Because I mean it was parameterized by t, isn't it? So x and y it was equal to t, so t is again going to be equal to 1. So this is going to be 0 again. Okay. So the only thing now that needs to be checked for case 2 and case 3 is that whether I get the same ratio there at the point 1, 1. So now see dx naught by dt by p. P is say j. I'm going to change it. J. Q is y and this is x. Okay, and again these two I can write it as 1, 1, isn't it? These two I can write it as 1, 1 at the point 1, 1. Okay, fine. And j, now it is given by 2t, so in the second case it is going to be 2, right? So this was what? Dx dt, dx naught dt was what? This was 1.
Yes, sir.
This was 1. Okay, and obviously from here itself I can say that what? That condition is not going to be satisfied anyway, isn't it? I want V to be along with the same direction of the tangent, isn't it?
Yes, sir. Yes.
Yes, sir.
So it is not going to have any solution. And in the third case, this is what? Sine pi t by 2. So this is again going to be 1, 1, 1. I think this is going to satisfy or not? Third case, are they going to be the same? Just a minute. Sorry. Second case is sorry. Second case is z equal to t. First case we have already done. Second case is z equal to t, isn't it? So if z equal to t, then what is going to happen? At the point 1, 1, because x and y is also equal to t. So eventually, the second case is going to give me the same ratio for everything. Are you getting my point or not?
Yes, sir.
Yes, sir.
So in the second case, I am going to have infinite number of solutions. Okay, and you can easily check, and that in the third case, you are going to have no solution. You are going to have no solution because of that sign thing. because you have to take the derivative of that, isn't it? You have to take the derivative of that for this. Okay, this is going to give you some 0 or something like that. Okay, so they are not going to be equal. So again, there is another interesting example. X zx y zy. To z yz equal to z xt yt, and this is what we have been given. This is fine, and I have been giving z equal to something like f of t on the initial graph. Z equal to f of t on C. So now the problem is you have to determine the class of functions ft for which our condition is satisfied. Our condition, that means this is related to this condition. P dy dt minus q dx dt. Of course, this is equal to 0 at the point x naught y naught. Okay, for this condition to be satisfied, what must have happen to the like function f of t? And you will see that this is pretty much straightforward. This is pretty much straightforward because your p is what? P is x, right? P is x, and q is y. Can you work it out at home? Let me see whether I have done everything all right or not. X zx plus y zy equal to z, x equal to t. Condition 4.4 is satisfied. Just let me know. So okay, not only this one. They are telling you to see under which condition this is satisfied. B is something like mu r prime t. Can you check that? Can you check that? See, basically then what is going to happen? Say dx naught dt equal to dy naught dt. I'm going to have this, isn't it? Is it okay? Fine. And dx naught dt, this is simply equal to 1. And p is what? P is say x is t. So dy naught dt, it is again equal to 1. Q is y is again t, and dz naught dt, this is simply what? F prime t, r is z. Z on the curve C is f of t. Are you getting some hint how to find out f of t? Yes? Simply solve this.
Linear f will be a linear function of t.
Yeah, simply solve this. Yeah. So it is going to be not even linear, it is going to be constant multiple of t.
Yes, linear passing through 0, 0.
So that's it. So now I'll come to a very interesting concept. So initial rule problem for conservation laws. So the initial rule problem for conservation laws, the development of SOX. Okay. So what I'm going to do, let me take this. First order PDE, and of course subject to the initial condition J, your x0, this is equal to f of x. Okay, so basically that means the initial curve, your c tilde, you can parameterize it through, the vector given by something like t 0 f of t. Okay, fine. So now, if I want to solve this problem, you already know that from our classes earlier, you already know that what is happening here. This initial problem always have a unique solution. This always have a unique solution. Okay. Now, how do you find out that unique solution? As before, what we are going to do, simply we are going to rope in the auxiliary equations. We are going to rope in the auxiliary equation given by this dy equal to dy by 1, dz by 0, and from here you can see that from the last equation, we are going to get something like z equal to c1, okay. So the first integrals say u x y z, I can simply write it as j, okay. And from these two, once you plug in your z equal to c1, so then I can write it as dx minus ac1 dy equal to 0, and from there I am going to get x minus azy equal to c2, right? And the corresponding first integral of the vector v, whose components are nothing but a of j, 1 and 0, so that I can write it as x minus a j 1. Okay, fine. So now you know how to solve it. So how to solve it? From these two, what we can do, we can write down the values of capital U1 as a function of t using the initial curve, okay. So then it is going to give me U1, this is equal to simply f of t, and then capital U2, that is going to give me what? Because see, x is t, and whatever may be the value of aj, you know that y equal to 0 initially. So you are simply going to get U2 equal to t, right? And that gives me a functional relation. From these two, and that is given by U1 equal to f of U2, right? U1 equal to f of U2, right? And from here, what I can do, I can get the solution. In the form your j equal to small f, your x minus az y. Is it okay with everybody? Fine. So now I still want to keep these two. I'll be coming back to that in a short while from now. Now, okay, so let me write down the okay, fine. So f of your x minus is y, okay, fine. So let me call it as a. So now let me come back to these two. You know that, I mean, we'll be able to find out these constants C1 and C2, I mean, based on the initial conditions given, right? So now if I impose the initial condition, say suppose initially your x was equal to x now, right? And then anyway your y is always 0, and Z is given by say f of x naught. Say suppose I call it simply Z naught. I call it simply Z naught, right? So then what I can do, like these two, I can simply write it as Z equal to Z naught, Z equal to Z naught, and from here I can write x minus a of Z naught, which is y, okay, and that is going to be equal to what? Its value, I'm going to take it, its initially whatever its value is going to be, right? So what it is going to be? It is going to be simply your x naught. It is simply going to be x naught, because what is going to happen here? What is going to happen here? Here, if you plug in a z y initially, so then I mean y is 0, so I'm going to get these two. I'm going to get these two, right? So if I call it b, so then you know that your a and b, they are equivalent, isn't it? A and b are equivalent. Okay. So why A and B are equivalent? See, if you look at A, what it is giving? It is giving me Z implicitly as a function of x and y. Okay, and from there I can get a surface. Right? And again, on that surface, what I can do? I can consider this b, and if you carefully look at the equation b, so what does it signify? If you look it carefully, see the second equation, it is nothing but a straight line in the xy plane, right? And the first equation, it is nothing but the plane z equal to z naught, right? So basically what it is going to do, it is going to represent a straight line on the plane z equal to z naught, whose equation is given by this. Is it okay? So basically a straight line, something like, say, suppose I have this is xy, and suppose this is j, and suppose I mean this is the straight line. Suppose this is the straight line. This is x naught. Say suppose this is the straight line. Your x minus a z naught y. This is equal to x naught. So if this straight line lie on the xy plane, so the straight line given by this b is simply going to be a line parallel to this, so such that this is elevated by z naught. So that means this is nothing but z equal to z naught, and then x minus a z naught, y equal to x naught. Okay, is it okay with everybody? Fine. I hope this is clear to you. Fine. So basically, what is going to be b? B is nothing but a straight line. B is nothing but a straight line, or to be precise, it is an integral curve, straight line representing an integral curve, lying on the integral surface given by A, corresponding to the vector V, whose components P, Q, R came from the given differential equation. Okay, fine. So now again, from that theorem, you know that the unique solution of the given equation, it lies in the neighborhood of some point. Here that point is not specifically given, but from the initial condition where I have got y equal to 0, from there I can say that I am seeking the solution of the given differential equation in the neighborhood of mod y tending to 0. Fine? Okay. So now what is happening? If I want to write A as a level surface, what I can do, from A I can write it as this U, say xyz. So this is equal to your z minus f of x minus azy. This is equal to 0. Is it okay with everybody? Fine. So now what we can do, let us verify whether the solution that we have obtained, whether it satisfies the given differential equation or not. Okay, and the differential equation, it was az jx plus jy. This is equal to 0. Okay, fine. So now again, you know that in order for having an implicit relation expressing j as a function of x and y, I must have your uz not equal to 0 in the neighborhood of mod y tending to 0. Okay, so now if I want to find out uj, so then you'll see that this is 1 minus f prime x minus azy. Okay, and then again derivative of this argument with respect to j, and that is nothing but minus a prime j y. So eventually this is going to give me a prime j y f prime x minus a j y. Okay, fine. See, so that means what is happening here? You know that I am seeking the solution in the neighborhood of this, So when y tend to 0, when y tend to 0, so that means you know that this is going to tend to 1. Okay, this is going to tend to 1. Okay, and if so, that means if I can keep this expression strictly greater than 0, So then what is going to happen? Your uz in the neighborhood of mod y tend to 0, it is always going to be positive. Okay, fine. Now, if you want to find out, say, ux is simply going to be minus f prime x minus azy into 1. So it is simply going to be that expression itself. Okay, and then uy again minus f prime x minus azy, and again derivative of partial derivative of this argument with respect to y. So that is going to give you minus a of j. So eventually it is simply az f prime x minus az y. Okay. So now if I want to find out your jx, so jx, it is going to be simply your minus your ux by uz. Similarly jy, it is going to be minus uy by uz. And then what is happening here? It is very straightforward. You have to just rope in this in the denominator. Okay. Now, if you plug this back in, here, you can see that on the left hand side, if you substitute the values of zx and zy, that expression that is going to reduce to an identity. That you can check at home. I'm leaving it as a homework. Okay, fine. So this is about the solution of this equation. So I just really want you to have a look at this, because next time I'm going to work out an example where this is going to come in handy. I'm not going to actually do all the steps to solve it. I'm directly going to substitute the final expression. Okay, so both A and B are going to be handy. Both A and B are going to be handy. Okay, so before moving to the next example, example corresponding to this kind of situation. So I want you to introduce it to the concept of development of shocks. Concept of development of shocks. So I have already shown you. The practical, not D, a practical example of shock where I had shown you a bullet being released and then some kind of shock in the shape of a ball, right? So you have already seen that. Okay, so you got to believe me, or probably you already believe me, that really shock exists in the real world. Okay, so I'm going to give you a mathematical insight into that. Okay, fine. So for that, so let me just stick to the same problem. Let me just stick to the same problem. Okay, fine. Okay, so I have already explained it to you. That this B, what does B indicate? B indicates the presence of an integral curve. In this particular case, it is a straight line. Presence of a straight line, right? Which lies on the integral surface, right? On the integral surface given by A. Fine. So now, see, if I consider, say, in say xy plane, if I consider in the xy plane, my situation is something like this. Say, suppose this is the point x naught, right? And then this line is x minus aj naught y. This is equal to x naught, aj naught y equal to x naught. And what is happening along this line? What is going to happen along this line? Your z is going to remain as z naught. Is it okay with everybody? See, what I want you to take notice is that, say, suppose my z-axis is in this direction. So can everybody see it? So this black pen which I am holding like this. So this one is the z-axis, right? Is it okay with everybody? Fine. So now, so that means what is going to happen? If you look at the scale, right? So the scale will represent that spatial straight line which lies on the integral surface. Okay. So what is happening on this spatial straight line? You know that along this line the value of z is equal to z naught. So basically the height of this straight line on xy plane, it is going to be simply z naught. So basically the length of this plane is going to represent z naught in this particular case. Is it okay with everybody? Fine. So now this brings me to the concept of your shock. Okay, let me explain it to you how your shock is going to form. Okay. So now suppose I consider 2 points here along x-axis. So this is x1 and x2, say x1 and x2. Okay, and let your z naught, this is equal to f of x1 and z1 equal to f of x1 and z2 equal to f of x2, say. They are nothing but the initial conditions. Okay. So then what is going to happen? What is going to happen? Now if suppose AZ1 is strictly greater than AZ2, right? So then what is going to happen? The straight lines given by AZ1y, this is equal to x1, and x minus AZ2y, Z2y, this is equal to x2. These two straight lines, they are going to have different slopes. Is it okay? Fine. So that means what is going to happen? Like say, eventually, these two straight lines, they are going to intersect at some point, say x0, y0. It's fine. Okay. So now let us see what is happening out here. So maybe I can give you a so this line is z minus a z2y equal to x2, and this line is z minus a z1 y equal to x1. Okay, fine. And if you want to find out the y coordinate, of this point, so then what I can find that through by simply plugging in the values here. Okay, so that is going to give me, say, from here y0, I can write it as your x1 minus x2, because this is negative, this is going to come out later on, AZ1. Okay, in fact this expression is very important in the context of development of shocks. Okay, so when we are going to parameterize these two curves, okay, from these, what happens? So generally, in all practical problems, this variable y, it designates time. Okay. So from this expression, what you can do, you can find out the time, the first instant at which there is going to be the development of a shock. So that is why that term is very important. And this expression is also sometimes called shock condition. It is also called shock condition. Okay. So now you may be thinking, how the shock is going to develop? How the shock is going to develop? See, what is happening out here? See, remember, I have assumed that your Z1 is not equal to Z2. Z1 is not equal to Z2. So what is happening here? Now, corresponding to this straight line, this green straight line, I am going to have suppose something like this. I am going to have something like this. Okay, this scale representing a straight line in space, isn't it? That is nothing but this straight line given by z minus a z1 y equal to x1, comma z equal to z1. Is it okay with everybody? So this length of this plane represents the height z equal to z1, right? So similarly, what is happening here? This straight line, okay, this straight line, it is at the elevation represented by the length of this pencil. Is it okay with everybody? So that means, see here, their lengths are different. Is it okay with everybody? Fine, because Z1 is not equal to Z2. You know that. So that means what is going to happen? At this particular point, I am having what? The value of z as a function of x and y, which are different because the lengths are different, isn't it? Because z1 is not equal to z2. So that means I have a discontinuity out there. Is it okay with everybody? So that means I have a discontinuity there, right? I hope it is clear to everybody. Okay, so that means that is what is called a shock. Okay, so that is what is called a shock. So this explains how a shock is developed. Is it okay with everybody? Fine? Okay. Now, let us take one example. Let us take one example. And again, see, although I told you that equations like this, I mean, it represents a conservation law. I still haven't told you anything about the physical explanation for that. Okay, so I will do it once I work out one particular example corresponding to the solution of this equation, and which is going to, I mean, exemplify the development of a shock. Okay, fine. So for that, okay, fine. So okay, so what I'm going to do here, so I'm simply going to take this problem. So j dash plus j y equal to 0, and your j x0, this is equal to minus x. This is equal to minus x. Okay, so now if I compare these two, then from A, you can see that the solution is given by j equal to c. The initial condition here, this minus x is nothing but f of x. Minus x is nothing but f of x. So I am going to get what? Instead of x, it is x minus az. Az was simply z, so zy. Clear? Is it okay with everybody? Just try to relate. This f. It came from what? It came from the initial condition. Earlier, the initial condition corresponding to this equation, it was z at x comma 0 was equal to f of x, right? Now my f of x is minus x. Okay, so minus f of, instead of x, it is x minus az into y. So, but here az is simply given by j. Fine. So this is okay. Minus x plus zy. Okay. So minus x plus zy. So this is going to give me z as your minus x by 1 minus y, right? 1 minus y. Okay, fine. And from here you can see that at y equal to 1, the solution has a discontinuity. Okay, so that is going to give you the shock. So you already have some idea about where the shock is going to develop. But again, what we will have to do? We will have to relate it to now a line lying in xy plane given by this. Okay, and what eventually in the xyz space given by both the equations of P. Okay, so now if I so these are going to be what? Z equal to Z naught. Okay, and x equal to x naught. So here what is happening? In fact, you're at when your x equal to x naught, z equal to z naught. In fact, that is given by minus x naught. Okay, but I'm not that much worried about that. So, and if I want to write down this equation, so that is going to give me what? X minus a z naught. A z naught equal to what? A z naught equal to simply a z equal to j from there. Okay. So a z naught is z naught and z naught is minus x naught. Okay. So it is going to give me x plus x naught y, that is equal to x naught. Is it okay with everybody? Fine. So now if you look at this equation, so how I draw it, say simply you have say x naught. Okay, I have already got 1 point, so if I get another point, then right, what I can do, I can make a straight line passing through those 2 points, and I am going to have my required equation. Is it okay with everybody? Fine. So now that you can check, okay. See, when x equal to 0, what is happening out here? Then you can see that y is equal to 1. Fine. So when x is 0, y is equal to 1. Okay. So what is going to be? No, 1 is not here. 1 is here. 1 is here. Okay. So okay, so this is 0, 1. Say, suppose this is x naught. Is it clear to everybody? Right? So now, suppose I change the value of this x naught. Suppose I change the initial condition to x1, say x1, where x1 is greater than x naught, right? So then what is going to happen? Again, this is going to be something like that. Okay? So again, this straight line, it is also going to pass through. It is also going to pass through this. It is also going to pass through this. Similarly, for some x2, again I am going to have something like this. Is it okay with everybody? So that means you know that at this particular point, if you take the corresponding z value, because right, z, see, if you look at this z naught, it was given by minus x naught. So here the z value is going to be given by simply minus x naught minus x1 minus x2. So basically, you have to consider them. You have to consider, say, suppose this is xy prime, so it is going to be below. Is it okay with everybody? Is the concept of shop clear to everybody now? Fine. Okay. So this represents the development of a shock. You know that the z direction is something like this. Okay. So here the corresponding straight lines, okay, in xy z space, it is going to be on that direction. Okay. Whereas in the general example, I had explained it to you, where it was towards me. Is it okay? Fine. Okay. So. And this one explains it very well. Because generally what happens, as I have told you, this y, the variable y, it is analogous to the variable time. And again, when I consider something related to time, I always assume that we have started from some initial time t equal to 0, and we see how the solution is evolving, right, as time increases. So when t greater than 0. Okay, fine. So now let me still stick to that. Let that equation be there. So now let me try to give you the physical reasoning behind the concept of what is conservation law. Why the conservation laws are going to be represented by equations like that. Okay. Okay. So for that, I am going to consider the example of traffic flow. Okay, traffic flow. Fine. So what I'm going to do here, I'm going to consider that suppose this is nothing but x-axis. This is nothing but x-axis. Suppose it represents a highway. Okay, and the traffic is moving in the positive direction. Traffic is moving in the positive direction. So that means from left to right. Is it okay with everybody? Fine. And again, this is a very good example because this traffic flow can be considered analogous to continuous, say, fluid flow also. Okay, so whatever concept that is being developed here, it can be, applied to other fields as well. Okay, fine. So suppose I am considering a location here, which is x, and that location I am considering at time t. Say, I am considering at time t. Okay, fine. So now let your rho xt, it represents the density of curve at the location x at time t. So basically what it does, it represents number of cars, your per unit length, number of cars per unit length. Okay, and again at the same point, let q xt, it represents the flow rate of cars. So that means it represents number of cars per unit time. Number of cars per unit time. Okay, fine. So now let me consider 2 points here, x1 and x2, 2 points here, x1 and x2. Okay, and then what is going to happen? See, in this portion, or in the interval x1, x2, if I want to find out the total number of cars, assuming that rho of xt is a continuous function, so it is say number of cars per unit length. Okay, so then in the interval x1, x2, my number of cars, it will be given by what? x1, x2. You have to simply integrate rho with respect to x, right, between x1 and x2. Is it okay with everybody? Fine. So now, then, if I want to find out the rate of change of the number of cars, so then it is going to be given by ddt of this x1, x2 dx. Okay, and that is going to be equal to what? Say this is what? Q was nothing but flow rate. And this is nothing but number of cars per unit time, isn't it? So it is going to be the difference between the flow rate at the location x1 and x2. So this is simply going to be your Q, your x1t minus Q x2t. Fine, Q x2t. Is it okay with everybody? Fine. Say like say this is being a one spatial dimensional problem. I mean, you may find it difficult to visualize the concept, but see, you can think about this. Say I can draw a portion of the highway like this. I can draw a portion of the highway like this. Is it okay? Fine. And traffic is moving from left to right. So you consider a location. Corresponding to x equal to x1. So here, obviously, at time t, some numbers of cars are going to reach this location, isn't it? Similarly, at the same time, some cars are going to reach this location, isn't it? from there, definitely, I can find out the number of cars per unit length, isn't it? If I have some say reference origin, isn't it? From there, definitely I will be able to find data. So similarly, if you want to find out number of cars per unit time, so what you do, you station yourself at this particular location, right? And then you count. I mean, how many cars have gone through that point? Say, suppose in I mean half an hour, right? So then from there you can easily find out the number of cars per unit time. Okay, fine. Now you have understood the concept clearly. I hope you have. Okay. So then what we can do? From now from this equation, what I can do, I can write it as your x1, x2, your d-rho, dt. So the arguments are in x, t. I'm omitting here. So dx, and this is going to be equal to your minus x1, x2, your dx, okay, dx, and this can eventually be written as x1, x2, your del rho del t plus del q del x dx. This is equal to 0, right? And now, because you can see that the integrand is arbitrary, so that is why from here I can simply write dt. This is equal to 0. Okay. Now you may be thinking, right? I have told you that the conservation laws are going to be something like that. It is always going to be something like that, and it is not yet in that form, right? The equation that we have arrived at, it is still not at. It's still haven't reached, I mean, that particular format, isn't it? Fine. So now in this particular case, you can see that this qxt, which is nothing but the flow rate qxt. Now, the number of cars per unit time, what is going to happen? Like, it is going to depend upon the speed of the car, isn't it? The velocity of the car, not necessarily speed. Velocity of the car, right? And it is going to depend upon what the car density is, isn't it? If there is heavy traffic, then, I mean, naturally, the cars are going to slow down, right? And if there is less traffic, definitely the, velocities of those cars, they are going to increase. Is it okay with everybody? So that is why this flow rate, it is going to depend upon the velocity. So as such, I can assume that it is a function of some. It is a function of the density. Fine. It is a function of density. So what is going to happen now? If I substitute in this equation, that this is going to give me, plus del x g of rho. Okay, let me maybe xt rho xt. This is equal to 0. This is equal to 0, and then you know that here what I can do eventually I can get it in some form like a xt del rho del x. This is equal to 0. Is it okay with everybody? So now you compare this equation and this equation, and this equation. So what is happening? Basically, here the coefficient of z dash we earlier designated as it is a function of x, y, z, right? So here also, this is, this is C. This is not only, it is going to be, this is going to be This is going to involve rho as well. Is it okay? Fine. So now you can see that all the variables are here. So here instead of y, I have t, isn't it? And there, j was the dependent variable. Here, rho is the dependent variable. Fine. Is it okay with everybody? Okay. So now I hope this concept of conservation law is clear. The development of shock, fine. All the things are clear. So what you do, you do the exercises in the top book. You do the exercises in the top book. And what I'm planning to do, although I mean today your classes are formally over, so I still try to maybe, the video record, 2 more lectures, and I'm going to upload them. Don't worry about it. The contents of those lectures, they're not going to be part of your NSEM exam. I'm clarifying that to you. Okay. So in that note, let me finish your this semester, teaching for this semester. Okay. I hope you are going to do great in your NSEM exam. Thank you.